Assalamu alaikum. As engineering students, most of us are familiar with the concept of microprocessors. In this project, I have worked on the design of a simple CPU known as SAP-1. To understand the basic structure and the operation of CPU in practice, I have designed this project. The key focus of this project was to implement the control sequencer in Logisim software, which allow the system to operate automatically. This project has been carried out through the part of our VLSI technology sessional course. I'm Fatara and my ID is 2008020. Now I'm going to present you the design and implementation of this project by using Logisim software. At first, I'm showing you the full architecture in both manual mode and automatic mode. This is my manual mode architecture, okay? And this is my automatic mode architecture. So before moving into automatic execution, I'll show you the architectural components that are required for SAP-1 implementation in manual mode and explain their purposes one by one. Let me show you the general purpose register. This is my general purpose register which hold the temporary data and are used for arithmetic and logical operation. Then ALU, arithmetic logic unit. This performs the arithmetic operations like addition, subtraction using the data from the register. Then I'll show you the program counter. This is the program counter and the program counter keeps track of the instruction address and the increments automatically after each instruction. Then I'll show you the decoder 4 into 16 decoder. This decoder convert a 4-bit output into one of 16 unique signals to identify the instructions. Then I will show you the SRAM cell. This SRAM cell, this is the basic memory storage element where a single bit of data is stored. Then I will show you the 16 4 into 16 SRAM. This converts a 4-bit output into, this is our SRAM 16 into 8 memory. This is the complete memory unit where instructions and data are stored for program execution. Then I will show you our instruction register. This is our instruction register. Okay, you can see this instruction register used to store the current instruction based from the memory and separates the output and operand. Then I will show you the ring counter. This is our ring counter. And the ring counters generate timing signals from T1 to T6 to control step-by-step execution of instructions. Then I will show you the instruction decoder. This is our instruction decoder. Okay, this instruction decoder decodes the output from the instruction register and activates the corresponding instruction line. Then our final unit is control sequencer. This control sequencer combines the timing signals and decoded instruction to automatically control the fetch, decode, execute cycles. Okay, now at first, this is the main architecture. Okay, at first, we'll prepare the RAM by storing all the required instruction and data. For this, I'll enable the control sequencer. Then I will turn on the debug pin. Then I'll give a pulse to PC reset to clear everything. Now the system is ready for manual loading. We store the past address 0. We set the address 000. Then I will toggle the marine manual pin. Then I'll give a clock pulse. Then clock pulse off. Marine manual off. The address 0 has been selected. Now I will give the instruction LDA13. The LDA13 has been decoded in my instruction table, which I have been showed in my GitHub. You can see for each instruction, I have given this table an address of instruction LDA13, LDB14, jump at STA halt. Now I will set the instruction LDA13 at address 0. Let me set this. Okay. So The LDA13 instruction is 000111101. Then SRAM write manual on, clock pass on, clock pass off, it is off. Then you can see the successfully at address 0, the instruction has been stored. Now I will do this same process for my another instructions. Okay, let me do this one by one. For address 1, I'll give marine pulse. Address 1 has been selected. Now I will give the LDB14. The instruction is 001, sorry, 101110. Then you can see this instruction has been stored. Now I will do this for my jump instruction at address 10. Okay, the instruction is 011000101. Okay, now I'll set this instruction. You can see this has been stored. Now I'll do this for my add instruction at 11 address. The address has been selected. Now I'll give the instruction for add, which is 0011000. You can see this, it has been stored. Now I'll do this for STA instruction at 100 address. My instruction for STA-15 is, I can see this from this table. This is the instruction. Okay. Instruction is 0101111. Okay. Now I'll do this for my fault instruction. I'm setting the instruction. You can see this has been stored at the address. Now, next we have to load the data values which will be used by this instruction. At address, you can see from my table, at address 13, the decimal value 20 will be stored, and at address 14, we will store the decimal value 25, and the instructions are here. Okay, let me do this. I'm selecting the address 13, which is 1101. The address has been selected. Now I will give the instruction for decimal value 20, 000100100. You can see this has been stored. Now I will do this for address 14. Let me select the address 14. This has been selected. Now I'll give the instruction for 25 decimal value, which is 0011001. Okay, you can see here. Let me show you. From here, you can see The instruction and data values have been successfully placed into the RAM and the processor is ready to execute them step by step. Okay. Now we can use the control sequencer automatically to fetch, decode, and execute the program. For this, we need to first turn off the debug pin. Then we can use it for manual mode. Then we give a pulse to PC reset. Okay, so the execution starts from address 0. In this program, there are 5 instructions and each instructions requires 60 states. This means in total, we'll need around 30 clock pulses. After every 6 pulses, one full instruction will be completed. So let me show you. After giving 6 clock pulses, okay, after giving 6 clock pulses, you can see register A has loaded the value 20 in binary from memory. Then giving after 6 pulses, you can see register B loaded the binary value of 25 from memory. Then giving another 4 pulses, okay, you can see, let me show you, the register A loaded the add instruction and the sum appears to the register A. Then next, I will give the more pulses to store the sum value in address 15. Okay. You can see the sum appears to the 15 address. Okay, finally after giving the another pulses, the halt execution will be start and the program stop execution. Okay. Now I'll move to our automatic mode architecture. This is our automatic source. This is our automatic mode architecture. Here we no longer load instructions manually. Instead of this, we use additional components like the program counter with loader. You can see. Then we use the instruction loader, program counter loader to transfer code from ROM to RAM, and an updated instruction decoder which also supports the jump instruction. The control sequencer, let me show you. This control sequencer has also been updated for the jump instruction with so many logical operations. To prepare this, I have built an assembler. Let me show you my assembler. This is my assembler. Okay, this assembler converts the assembly code into hexadecimal. The program shown into the table compiled into the hex. You can see this is my table. This has been converted into the hex code. Now I'll copy this hex code and paste into the, then I will set it into the RAM, so that after I'll paste into the ROM by editing contents. After this, we need to transfer the ROM content into the RAM. Let me show you how to. This is my main architecture, and this is my ROM, and I'm going to, by being edit contents, we can see the hex code is pasted here. Okay, this has been done. After doing this, we need to transfer the ROM contents into RAM. For this, we have to turn on the debug pin on. Then we'll give a program counter pulse to reset everything. Then each instruction needs 2 pulses. One pulse to set the RAM address and want to transfer the data. Since our RAM has 16 locations, we give 32 pulses in total. After 32 clock pulses, all instructions and data will be successfully loaded into the RAM. Let me show you. After giving pulses, if you see carefully, all the instructions are going to the required address. Okay, let me show you. From here, you can see our is all the instructions and data are successfully loaded into the RAM. Now, we'll turn off the debug pin. So, it can prepare for the execution. For execution, we reset the program counter again. Now, we'll give the clock pulses. So, we have 6 instructions. Each one requires 6 T states. That means 6 clock pulses will complete 1 instructions. After giving first 6 pulses, you can see the register A loads the value 20 in hex 14 from memory address 13. Then after giving another 6 pulses, you can see register B has been loaded the binary the register B has been loaded the decimal value 25 in hex 19 from memory address 14. Then giving after 6 pulses, the program counter will be jumped from address 2 to address 5. Let me show you this. Okay, you can see this. The program counter has jumped to the value address 5 and the instructed by the jump command. Next, after giving 6 pulses, okay, you can see the register A has been loaded the add instruction and the result 45 in hex value 2D is placed into the register A successfully. Then after giving another 6 pulses, okay, let me show you. You can see after giving another 6 pulses, the STA instruction stores the result into memory address 15. Okay. Then after giving the another 3 more pulses, the halt instruction executes and the program will be false. Okay. Now, in this way, the automatic mode successfully demonstrate the complete fetch, decode, execute cycle in both arithmetic and jump instruction handled by the control signature. Thank you for watching my video.